Hi everyone, I'm Nithini Chaturya and welcome back to my YouTube channel as Optimize. In today's video, we are going to talk about Heap Tree Priority Queue. We are going to learn what a priority queue is and how to implement it using Heap Tree and how we can perform enqueue and dequeue functions to add or remove items from the priority queue. Finally, we'll go through a simple example to see how the priorities determine the order. Without further ado, let's see what is a priority queue. A priority queue is a queue where each element is assigned a priority. As you may already know, the FIFO queue follows the first in first out principle and the LIFO queue, which is also known as stack, follows last in first out principle. Unlike these two types, in a priority queue, the element with the highest priority is always served first. For an example, imagine a hospital queue. The patients with more serious conditions will be treated first, even if they arrive later than the others. There are two main types of priority queue. The first one is mean priority queue, where elements with lower values have higher priority, and the second one is max priority queue, where elements with higher values have the higher priority. Now let's see how a heap implements a priority queue. Heap is a tree-based data structure and its ability to quickly access the highest or lowest priority element makes it perfect for implementing a priority queue. Because of the simplicity, efficiency and functionality for priority-based operations, the binary heap is the most common implementation of a priority queue. There are two main types of heap, which are min heap and max heap. In min heap, the parent node is always less than or equal to its children. So the root node will be the minimum value of the heap. And this type helps efficient retrieval of the smallest value. In max heap, the parent node will always be greater than or equal to its children. So the root will be the maximum value, and therefore this type is used to retrieve the highest value efficiently. Therefore, the min heap is used to implement the min priority queue and the max heap is used to implement the max priority queue. The binary heap is usually stored in an array where the root node is stored at index 0 and the left child node is stored at index 2 into I plus 1, where the I represents the index of the parent node and the right child node will be stored at the index 2 into I plus 2. For example, when storing this heap in an array, first the root will be stored at index number 0. And for 11, to find the index of this, we can use this equation because 11 is the left child node of 10, which is the root. So we can replace I with 0 because it is the parent of 11. We can get the answer like 1. So the position of 11 is at index 1. And as for 13, we can find the index by solving this equation because it is the right child node of 10. So we can again replace I with 0 and solve this equation to get 2. So the index of 13 will be 2. And for 14, which is the left child node of 11, we can simply replace 0 with 1 and solve this equation to get the answer as 3, and so the 14 will be stored at index number 3. And finally, this heap is stored as an array like 10, 11, 13 and 14. Now let's see how the NQ operation works. Step 1 is to add the new element to the end of the array or the heap. Step 2 is to compare the new element with its parent and swap the places if needed. This process is also called as shift up or heapify up. If the new element is added to a max heap and it is larger than its parent, it means that the new element has a higher priority than its parent. So the new element should swap places with the parent. And if the new element is added to a min heap and the element is smaller than its parent, it means that the new element has a higher priority than its parent. In here also, the new element should swap the position with its parent. We should repeat this process until the new element reaches its appropriate position. In here, we have a min heap as well as a max heap. When we perform NQ operation to the priority queue, let's see how each heap will change. As the first step, we have to insert the element at last of this heap. And for the second step, we have to compare the new element with its parent to determine if it is in the correct spot or not. In a min heap, the parent has to be always less than or equal to its children. So, in here, it violates the heap property. So, we have to swap the new element with its parent. And then again we have to compare 30 with 10 as 10 is the new parent of 30. And we can see that it doesn't violate the heap property in here. So the heap is now heapified. In here, a max heap, the parent has to be always greater than or equal to the child node. So, here the new element violates the heap structure, so we have to swap these two also. So this becomes 30 and this becomes 20. And then when comparing 50 with 30, we can see that it does not violate the heap property. So we can say that the heap is heapified. And the priority queue is correctly enqueued. Next, we can discuss how the dequeue operation works. When we perform the dequeue function in a priority queue, the element with the highest priority will be removed first. With that in mind, let's see how these heaps change when we perform dequeue function in a priority queue. For the first step, we have to remove the root node because the root node always consists of the highest priority element. So we can remove these. And the second step is to replace the root with the very last element, which is the rightmost leaf node. So we can replace root with 31 in here, and in here we can replace it by 8. And the third step is to remove the last node to make the heap smaller in size. Then we can see that this heap now violates the heap property because in here the parent node is not less than or equal to its children. So we can swap this parent with this and it becomes 31. This becomes 20. And we also have to compare these two. And when comparing, we can see that it does not violate the heap property. So we can tell that this heap is heapified. In here also, because this is a max heap, the parent node should always be greater than or equal to its children, and that property is violated in here. So we have to swap these two also. So this becomes 40 and this becomes 8. And we have to also compare these two nodes, and we can see in here also it violates the heap property. So we need to swap those positions also. So here will become 10 and in here it will become 8. Then we can see that the heap is properly heapified. Because of that, we can say that the dequeue function is properly carried out from both of these heaps. Finally, let's see an example on how the priorities determine the order. Here, I have assigned some tasks with priorities to implement a min priority queue. Task A is assigned 5, task B is assigned 2, task C is assigned 8 and task D is assigned 3. First, we have to insert these tasks into a min heap to carry out the enqueue process of the min priority queue. After the enqueue process has been performed, the min heap should have preserved the heap property, and because this is a min heap, the root should be the minimum value. Here is the illustration of the heap after performing the enqueue method. Thereafter, we have to perform DQ method. Task B will be processed first because it is the root element. After that, the heap will be reformed as explained in the DQ operation process. Each time that we perform the DQ operation, it will remove the root from the heap and then reform the heap properly. So, the order of the tasks performed will be B, then D, and then A, and at the end it will be the task C. Now we can see that to determine the order of the priorities, it doesn't matter which element was inserted first. The only thing that matters is the priority level of each element. If you found this video helpful, don't forget to like and subscribe for more content. And if you got any problem or feedback about this content, please feel free to leave a comment. Thank you for watching and have a nice day.